Thanks so much. Give me a second. Thanks so much and welcome. And I'm sorry I can't be there, but there were some travel issues. What I will present you here is the critical metals in VMS deposits. And those of you who have not been familiar, 1 second here. What's this? The next? I just want to go to the next slide. Those of you who haven't been familiar with VMS deposits, they are defined as weather-bound to stratiform accumulations of massive to semi-massive sulfides on the seafloor, and they are polymetallic. They are mostly mined for copper, zinc, less lead. There's also some deposits that are enriched in gold. But in recent years, they have been also looked at for the critical metal content because, as you will see, they actually can have quite a high amount of different critical metals. Age-wise, VMS deposits range from the Archean to today, so we find them actually on modern vents. And this model here shows the principle of how we form VMS deposits. It's a plumbing system. You practically suck in ocean water that gets heated by the upwelling mantle or an intrusion, and then you leach base metals like copper, zinc from the wall rock, and once this ascending hot fluids reach the ocean floor, they react with the cold seawater that changes the conditions and the massive sulfides drop out. So VMS deposits in Canada have been played historically a large role, and we find them actually in almost all provinces. Since the geology of the large scale is very similar between Canada and the US, a lot of those belts that are shown here for Canada actually extend in the US. So the superior cratone that we have here in Ontario, as well as in Quebec, extends to Wisconsin, etc. So a lot of VMS deposits, at least historically, are also in the US. Then we have the Paleozoic Appalachians that run from Newfoundland down to the Appalachians, with several big VMS districts on both sides of the border. And then on the west, we have the Cordillera with quite a few VMS deposits that also stretch into the US, mainly Alaska. So when we compare the critical mineral list from Canada and US, which I did for the talk, there's not too many differences. So Canada is here on the left, US on the right, and you see that a lot of minerals that are classified by both countries, highlighted here in yellow, are actually found in VMS deposits. So bismuth, antimony, cobalt, indium, tellurium, tin, nickel are very common in these deposits. Arsenic, which is a critical metal in the US, is listed here. And for Canada, copper and zinc play a huge role, and we have it actually also on the Canadian critical mineral list. And these are, as I mentioned, the main commodities in VMS deposits. The problem we have with VMS deposits, however, when it comes to the critical metal content, a lot of the data we have are vintage data that have not any analysis of critical metals. That relates to analytical processes, even now that the standard methods that applied by mainly industry can include that, we have still faced that issue. They dissolve not all components that can be critical metal bearing. The other issue is once you run those methods, the commercial labs not always have appropriate standards and reference materials to check for QA/QC. So the question arises, how reliable is it? And that, of course, has also implications. What is reported in feasibility reports like York or NI 43101? So we don't have necessarily a grade or resource, including tonnage for these critical minerals, which makes it often hard to assess it for the economic potential. And from a geologic perspective, and I will talk about that a little bit, we don't know in what minerals actually the different critical metals set. They sometimes, not always, form individual mineral phases, but their content in base metal sulfides is very poorly understood. So what I will present here, two examples from Canada. One is the Ming mine in Newfoundland. So Newfoundland is on the most eastern part of North America. And the Ming mine, which closed in 2023, is actually a copper plus minus gold VMS deposit of Campro region H. You don't have to remember all these zones, but we have, that's not uncommon, different ore lenses highlighted here in a plaque. The interesting thing is they are all deformed and metamorphosed to upper green schist conditions. That's why we have them dipped up to 35 degrees to the northeast and quite stretched. When we look at actually the content, because I analyzed the base metal horizons for also arsenic, antimony, and other critical metals at the time, we see that there's a big difference between the ore lenses. Arsenic, antimony are enriched in one of them, and that has to do with the mineralogy, as I will show you in a moment, where other lenses are more enriched in tellurium, bismuth, to a part also selenium. And that again is a reflectance of the mineralogy. And detailed mineralogy shows that the reason why we have tellurium and bismuth in some of the zones, because they occur in tellurides in form of, as shown here, symplectides with galena, either altaite, which is a lead telluride, hazite, silver telluride, bismuth tellurides like bismuthenite, etc. And then on the other side, the zone that was more enriched in arsenic and antimony, because it's so enriched in tennantite tetrahedrite, which is a sulfur salt of the arsenic and antimony end members. We have also, between sulfur salts and tellurides, we have several antimonites in it, also trace oxide in form of tin. And interestingly, no matter if your ore lens is enriched in tellurides or in sulfur salts, they all occur very closely to gold electrum, and often in the symplectides, which are irregular intergrowths that are often interpreted as sulfide melts due to coarse bimetamorphism. So, as I mentioned, we can easily look up, okay, what exotic minerals do we have? Are they critical metal bearing? But in recent history, we also look actually at the base metal sulfides and what is the critical metal content of those. And here, the antimony tellurium bismuth was analyzed in pyrite, chalcopyrite, sphalerite, arsenopyrite, galena from the different ore bodies listed here. And what you see is actually that the values in these minerals vary greatly. Antimony up to 50 ppm in most minerals, but then we go to arsenopyrite and galena, completely different picture that has to do with replacement. Antimony and silver can go for lead in galena, that's very well known. But we have also areas where tellurium is highly enriched in pyrite. Why is that so? Does it has to do with higher arsenic content? Is dislocation or pipe diffusion a process? These are processes that occur on the grain scale that are not too well understood at the moment. However, what a lot of these elements are, antimony, tellurium, bismuth, they are of magmatic origin. We find them very often in epithermal deposits, so that is slightly different than where copper and zinc come in VMS deposits that are historically and knowingly known from being leached from the wall rock. 1 second. So now I switch to one of the biggest deposits we actually have, the Kidd Creek deposit, still in production, has been mined for nearly 50 years. It's supposed to be shut down at the middle of next year. And this deposit is of Mesoarchean age, bimodal felsic, mainly zinc and copper with some silver, also metamorphosed, green schist facies. But why it is so interesting from a critical metal content, because it has quite a bit of indium and tin. And you see here VMS deposits in the triangle. Kidd Creek is one of the highest in both concentrations. And the interesting thing is when we look at Kidd Creek, which has several different ore bodies, they all have a zinc-rich interior surrounded by massive to semi-massive copper-rich bases. And when we look at actually the mineralogy again, here we have these sphalerite lenses that are also quite enriched in indium, as well as tin. We can actually see that there are differences between those contents. However, when we look at indium, I want to highlight that on average, 270 ppm indium was found in Kidd Creek. That is 3 times the magnitude of crustal average of indium, so quite enriched. And up to 2010, 50 tons of production of indium came out of King Creek annually, which made quite a big portion of indium globally. So when we look now at indium, and I apologize, I put a table in here, but Mark Hennington's work from the late 90s on it is actually the most recent study on that. Tin occurs both in the oxide as well as in the sulfide. And a lot of the cassiterite, the oxide, occurs with phthalate, so lower temperature system. And that is a little bit different to where we have tin as a sulfide in form of stannite, as well as indium as in rockquisite, which is with chalcopyrite, indicating that indium is transported with higher temperature fluid, and tin can actually vary in how we transport it, low and high temperature. So to come to the conclusions, when we look at bismuth, tellurium, and antimony, they are associated in VMS deposits that show bimodal magmatism, either bimodal felsic, bimodal mafic, and they are often there where we have also precious metals. This applies to Ming, and other deposits are listed here from Newfoundland. And bismuth, tellurium are known to be transported at fluids of higher temperature, around 300 degrees, where antimony is more lower temperature phase. And the fluids actually need also quite varying tellurium fugacity and molality of bismuth-antimony ratios to be able to transport these different critical metals. There's a close genetic relationship of these metals to gold and magmatic fluids, and more importantly, there's also an epigenetic upgrade of these tellurides and sulfur salts related to sulfide melt formation, because bismuth, telluride, antimony, especially when they occur close to or with galena, they can lower the melting point of sulfides down to 350 or even below 300 degrees. That's why we call them low melting point chalcophile elements. In contrast, tin and indium, we have with bimodal volcanism. There are other examples globally where we have them also in deposits where they actually occur with shales, like in the Iberian Pyrite Belt and the Bathurst mining camp in Nova Scotia, New Brunswick. And as I showed you, the temperature associations of tin and indium are both at low and high temperatures, depending if they are with zinc or copper. There is indication that we have a magmatic influence again, especially for indium. We see that quite a lot. Tin as well. Tin is also known mainly from intrusion-hosted deposit. However, since tin occurs in deposits, VMS deposits that are associated with black shales, we have not yet a good grasp related what is the significance of those very fine-grained organic-rich sedimentary rocks. 1 second here. I apologize that this technique did not work. Let me. Okay, let's try that. Going back. Okay, my last slide actually summarizes that critical metals are still quite underexplored target in VMS, because we still have not a very good understanding of the critical metal content related to incomplete whole rock lithogeochemistry and the standards needed to analyze for them. The mineralogy is coming more and more, but we still have quite a lack in the different deposits. And we have limited data available. What are the sources of the different critical metals? Are they leached from the wall rock similar to copper and zinc? Or do they have a magmatic origin because they are associated with precious metals? Or can they even be of a sedimentary source if this is part of the stratigraphy in VMS deposits? What more and more people do, and I'm one of them, is also looking actually on the impact of deformation and metamorphism. This is here on the bottom an image of EBSD on flint-flon pyrites, which is electron backscattered diffraction. And we see actually that there's a lot going on deformed sulfides and the movement of critical metals either out of their lattice or enrichment in certain parts of pyrite and other base metal sulfides. But we have not yet a good grasp what is the dominating process. With that, I thank you for listening. And if there are any questions, please feel free to either send me an email or ask right now. Thank you.